CLion, a cross-platform IDE for C and C++. Download now.
Hello, everyone, and welcome to my talk about contracts in C++26, which is actually part 2 of my talk from several conferences last year. There were lots and lots of topics I didn't have time to speak about then. So I decided to do this part 2 this year. This is the first conference I'm presenting at. And believe it or not, contract is a huge topic, so there are still leftovers. So who knows what comes next? As for myself, my name is Andrei Zissu. I'm a veteran C++ programmer from Israel. I currently work at Semperis. We are a unicorn focusing on delivering identity protection and resilience solutions, specializing mainly on protecting Azure and Active Directory, but also but not only that. I've been a member of the standard committee for the last 4 years and counting. And I've been particularly active in SG21, although I'm not one of the main authors of the contract proposal, but I've been there. Quick note about the way I'm presenting. I was planning to present live, but due to current circumstances in Israel, I didn't feel quite comfortable with that. So this is pre-recorded and also not at quite the high standard I was aiming for, due again to those same circumstances. I will, however, aim to be present afterwards in Gathertown, and also during this presentation, I will be active on Discord and answer your questions. I will start before going into the slides. I will start without a dedicated slide with some latest updates. So the current situation is that we have the contract subgroup SG21 is currently inactive since it's basically finished its work for now. And all contract discussions have moved into the evolution group, EWG. Contracts and C++26 in general are about to be finalized in Croydon near London 2 weeks from now. Since contracts are in the status quo, if no objection passes in plenary, we will be able to say that we have contracts in C++26 as a fact. There was the main, probably only thing being discussed in EWG since Kona, since November, was around an objection raised by the Romanian national body that have been requiring a form of contracts that are guaranteed contracts that can only be evaluated with enforce or quick enforce semantics. For those people that believe that they must have a guarantee in code that a contract will actually serve as a kind of control flow and protect the immediately following code. There has been lots of discussion about this. We have had numerous 2-hour telecons in EWG. Several proposals were considered, and ultimately none of them gained consensus. So we will be seeing in Croydon very soon. I'm quite optimistic that overall contracts probably still have quite a based majority there. But we'll see. So fingers crossed. So now let's continue to the rest of my presentation. We'll start by discussing some additional syntactic restrictions. The first one is in regard to preconditions and postconditions on member functions defaulted on first declaration. This is standard is for writing equal default in a class header. When you do this, you create a trivial declaration for those functions. They will be trivial functions. Trivial functions cannot do anything. Even if you replace that with an empty implementation, that's already not trivial. And of course, if you were to put a precondition on or postcondition on one of those, that would also make them non-trivial. So that's the first reasoning for this prohibition. The other one is that, of course, you could also have a turn violation handler, and that would also greatly possibly change behavior. As a simple example, we can see here a struct which has a defaulted copy constructor. And you can see that we can statically assert that it's indeed trivially copyable. Furthermore, we can see here that this only holds if the function is indeed defaulted on its first declaration. In our case here, it is defaulted, but it's on a second declaration. In the class header itself, it's not defaulted. Therefore, even in this case, it's already not considered trivial. So now that we've seen the problem, there were two solutions that were taken into consideration, and both were rejected. The first one would have allowed contracts to break triviality, as in once you apply such a pre or post condition to a defaulted function, it's no longer trivial. And this was, of course, rejected because it breaks contract design principles. It affects behavior which contracts are not allowed to do. The second one would have the compiler simply ignore the contract. The contract would go silent. This doesn't break the principles, but it's simply surprising and definitely not something we would want to have into a facility which people need to be able to grow to trust. So these were two bad choices. And until we come up with a better option, in such cases, we have another principle, principle 14, which says, okay, we can't make up our mind right now. So just make this ill-formed so that no one can do such a thing. No one can, in C++ 26, as per P2900, no one will be able to place a pre or post condition on a defaulted function. And we'll see about this later when someone hopefully comes up with a better idea. Now to another thing that we won't have in C++ 26, and that is pre and post conditions on pointers to functions. For the same reason as before, that we couldn't, that there are all sorts of problems that we'll see shortly, and we couldn't come up in time with a agreeable solution. So same as we saw before, we made this ill-formed. So you can see we have here a pointer to a function fptr. We cannot place pre and post on it, otherwise it's ill-formed. Of course, on a function itself, we can place pre and post, and if we call that function via the pointer to function pointing to it, we will get those pre and post checked as long as those checks are enabled on the callee side. We cannot get this kind of checks in C++ 26 on the caller side. So here are some of the issues we encountered that led to this decision. First and foremost, we need to decide if we want to have contracts on pointers to functions. We need to decide where we store them. There are two main choices. The first option is to store them as part of the pointer type. So any contract we apply to that pointer to function becomes part of the type of that pointer to function. This raises several issues. If we change the contract, we create a new type. If those types are used to instantiate templates, we get even more code bloat than template instantiations already create. Having different types also means different name mangling. And this would create incompatibilities as in ABI breaks. The other option would have been storing the contract as part of the pointer value. This means something that must happen at runtime, and it requires both space and time. Space because you need to somehow store that extra info, and you would have to go through function tanks. That's both space and performance. Or alternatively, you could have white pointers. White pointers is extra info. I'm not sure that that would incur any serious performance penalty, but it would create ABI breaks. So not only would any function pointer that we would add a contract to be ABI incompatible with its previous version, it would now be a new kind of function pointer, a wide, a fat kind of function pointer with additional information, which obviously would be incompatible with regular function pointers. And to be able to distinguish between them, they would at least need to be for different types than regular function pointers, which brings us back to having the information, or at least some of it, in the type system after all. So in this case, we've benefited nothing from also having runtime costs. Speaking of which, obviously, on the very definition, any approach based on pointer value would have some runtime overhead, and there is a P2900 principle that simply says that we are not allowed to do that. The third option would involve neither messing with the type system nor adding runtime information, but rather logically add some attribute to a variable, to the variable within the function pointer, which the compiler would be aware of at compile time and would make it add some caller side handling, obviously checking the contract. The problem here is that, okay, this is easy to do at locally, but if such a pointer needs to be passed to some other function and go through some call chain and whatever, then you're gonna need some back channel to convey that information, and that's no longer that easy or perhaps even possible to do, at least not without ABI breaks. And there is also an insurmountable problem with templates, which we'll see on the next slide. So as you can see here, we have two function pointers with the same prototype, other than the contract. The contract is different. And we apply stud invoke to both of them. Now, mind you, in this case, we haven't added contracts to the type system. Therefore, stud invoke sees the same type. And language rules require template instantiations of the same type to be identical. Therefore, the compiler is required to produce the same code for both invocations. Otherwise, that would be an ODR violation, which leaves us with no way of conveying that information and of doing and of applying the different contracts. And therefore, we can't use this path of attaching contracts to the variable type of pointers to functions with any leaving us with any way of having that work also with templates, as you can see. Another very interesting path forward, albeit only for C++29 at the earliest, it's coming from Lisa Lippincott, who is one of the main contributors to C++ contracts and to the C++ standards committee in general. She proposes introducing so-called function usage types, which would not be freely interchangeable with normal function pointers, and they would be able to be enriched with additional information such as contracts. And I liken them to, in a great part, to strong types, to the extent that those can be implemented today in C++. And in any case, those would be distinct from today's normal pointers to functions. And again, this was presented way too late for C++26. That's why she herself didn't propose considering this for C++26, and I do hope it will be considered as early as possible in the C++29 cycle. Okay, now on to our next restriction, which pertains to preconditions in constructors and postconditions in destructors. In both cases, in C++26, they will be prohibited from implicitly referencing this pointer, as in referencing non-static members of the current object. If they do want to do this, they have to explicitly use this pointer. All of this you can see in these examples. For example, here you can see the most interesting cases are the ones that remain well formed. So you can see all of the cases where we explicitly use these pointers are, of course, well formed. And also we have the two post conditions in a constructor, which are okay. And we have a precondition in a destructor, which is also okay. So now next to the motivation for this. So as I'm sure you know, referencing non-static data or function members from a constructor or a destructor, and especially from just before starting the constructor or just after executing the body of the destructor, those are very delicate issues, and they are very likely to result in undefined behavior. And one of our principles is that we do not want to introduce new undefined behavior via contracts. Now, it wouldn't exactly be the contract mechanism itself that would be introducing such undefined behavior, but it would be, in our mind, too easy for users to mistakenly introduce such behavior. On the other hand, we don't want to just ban such references because they do have some legitimate and safe use cases, especially around inspecting addresses without dereferencing them, but respective where an object is about to be constructed or has just been destructed, you can safely inspect its address as long as you don't dereference it. So we need to use the user to explicitly do this by using this pointer, and it's a way for the user to state, okay, I know what I'm doing, trust me. On now to some interesting semantic aspects of contracts in C++26. Moving on now to probably one of the most complex, tricky subjects you're gonna be hearing about today. So this is about objects, lightweight objects that per the current C++ standard, the compiler is allowed to optimize by passing them in as function parameters and as return objects via register. There are some eligibility rules for this. In general, an object needs to be trivially copyable and trivially destructible. But the point is that those things, in those cases, may be passed via register as either as function parameter or as returned object. And we can see the first example here, which pertains to a returned object. So we see that we have a function that receives an object by via pointer and does nothing with it other than verifying in the post condition that the address of the returned object is the same as the address passed in via that pointer. And in our case, we're returning a new object by value, and it's going to be elided into the object receiving it at the call site. So it should be the same address. However, this post condition is not guaranteed to pass. In fact, it may or may not evaluate as true because that returned object may actually be passed via a register, in which case those are going to be two different addresses to different objects. It's not going to evaluate as true. And we're going to have a contract violation. A very similar thing is happening here, this time pertaining to the input parameter. We have an object that's being passed in by value, and then we are assigning its address to a local variable. And then in the post condition, we are comparing the address of the input parameter to the same address supposedly that we have stored. However, when we initially capture that address of the input parameter for the benefit of the post condition, at that time it may still be in a register. Therefore, these two may not are not guaranteed to be equal in terms of address. They are guaranteed to be equal in terms of value, since the input parameter is const, and mind you, as I pointed out the last time, in order for an object to be eligible to be used in a post condition, I mean an input parameter, if it's being passed in by value, it must also be declared const for this exact reason that otherwise we would be unable to reason about this kind of assertions. So in most cases, this is good enough for us. We don't really care about the object address, aka identity. However, turns out that it's not absolutely always the case either. So here we have an admittedly exotic, but not quite entirely far-fetched example. We have a class random integer. It has two primitive members, and only one function. Now the members are mutable, so the one function, even though it's const, it's allowed to mutate them. And since other than that function, we have nothing else, this class is trivially copyable, trivially destructible. Therefore, such objects might be passed in via registers. And we are using this, we are referring to this input parameter in a post condition, therefore it must be const, yet it's able to call that function because the function, of course, it's const, yet the members are mutable, so it may mutate them, which indeed it does by assigning to them a random value. Now, we call this value function twice, once in the post condition and once when returning the object. But are these two the same objects? So when we are going to where we are going to do a bitwise end, which should result in 0 due to ending to equal values together. This will not necessarily be the case, because if the object was passed in via a register, then those are now two different objects. And even though we are caching the result and only doing this computation once, that's actually once per object, and those are two different objects. So if it's passed in via register, we are virtually guaranteed to get a contract violation in this post condition. So, what did we end up doing about this issue? Various options were considered, such as not allowing post conditions altogether, yay, or not allowing ODR using, as in referencing, function parameters in post, or not allowing ODR using function parameters in post if they are just by val, or if they are just by val, but the kinds that are eligible to be passed by a register, or the ones that are just by val and eligible to be passed by a register and also have mutable members, or allowing post conditions referencing just scalar types. You see where this is going. Another option would have been to not allow post conditions to see parameters on the caller side, but that would mean that they would have to see it on the callee side, and on some platforms that would basically modify the API. So what a mess. So the final decision was that this is indeed an exotic problem. Not that it won't happen in practice, but it's important to a small enough part of the community, if at all, that it's not worth all this huge mess. So let's just keep actually allowing it. So this remains possible in C++26. So beware of this, but again, you're quite unlikely to actually encounter it unless you do kind of out there stuff. On to our next topic, lambda captures and contracts. So the bottom line here is if you add by adding a contract to a lambda, you are not allowed to have that contract affect any capture that wouldn't have otherwise occurred. And that pertains only to implicit lambda captures, as in equal or ampersand by themselves. And this stems directly from principle 4 in P2900. That's zero overhead. You are not allowed contracts, especially ignored contracts, to have any influence on actual program. There is an exception to that, which is that exotic static members of template of class templates that would be instantiated by a contract. I think I briefly touched on that on my previous talk, but other than that, contracts are supposed to have zero overhead, and this is how we apply this to lambdas. We can see this in action here. We have here two cases which are ill-formed, F2 and F4. F2 is a precondition, F4 is a postcondition. In both cases, we have an implicit capture by value, and we are referring to I from a contract assertion, and there is no other use of I in that lambda, meaning that it would lead to I being captured only because of our contract, which makes this ill-formed. In the case of F1, we do have a precondition referring to I. However, I is external to the lambda, so there is no additional capture here, so we're fine. And in case of F3, we are also fine, even though we are causing an additional capture here due to the precondition. I is captured explicitly into the lambda, which would be a little odd actually without the contract. You capture something explicitly and then do nothing with it. So in this case, the programmer was explicit, which we see as a sign that they were intending to actually do this. So then it's okay, even though we are capturing something only for the benefit of the contract, it's being done explicitly, so it's fine. The reasons for having this limitation is that we're affecting behavior. Other than the obvious that in some cases, some object may be expensive to copy into a lambda, and the programmer may not have realized they were doing that. We may be affecting both the physical dimensions of the lambda, such as its size and alignment, and its traits, its type traits. It all of a sudden may no longer be trivially copyable or standard layout or what have you. So this is contracts affecting actual behavior, which, as we've seen numerous times, is something we do not want to allow ourselves to do. Next, we'll be discussing some aspects of how contracts are evaluated and how contract violations are handled. First, quick word on point of view. You've been hearing quite a bit about callers and callees, and you will even more during the rest of this presentation. This is the basic model. We have, for any function, we have the caller and we have the callee, that's the function itself. And both preconditions and postconditions may be evaluated on either side. This is the main reason why we have why we allow any number of evaluations for any given contract assertion, so that we can decouple contract semantics on either side. On now to the big topic of virtual function calls. Now, this was one of those topics that for some people there are must-have in C++ 26, even though it's a contract MVP only at this stage. Ultimately, we had to remove it after it was initially included into P2900 because it could not reach an ongoing consensus on how to do this the right way. There are several proposals, but we will have to see them for C++ 29. In other languages, contracts are inherited from base classes. So that when a derived class adds a precondition that basically provides further allowance for further types of input, therefore they widen the preconditions. And the reverse happened with postconditions. When you have a derived class doing something more precise, it that thing it basically promises to hold to some additional promise in addition to what the base class contract postcondition would be promising. In C++, after lots of arguing, it was decided that we have a principle one, that is stronger than the motivation for that kind of inherited contracts, which says that contract assertions must check a plain language contract, as in what the function verbally promises to do. If you write a function and you will probably write a comment that says what this function is doing, you want your contract to be entirely dependent on that, on what's in front of your eyes, and not on something that's out there remote somewhere in some base class. You want everything to be immediately visible. And as I was saying, this has been spurring lots of arguments, and those arguments are far from being settled at this point in time. So, in order to demonstrate one of the dilemmas faced by the committee and the prolonged arguments we've been having around this, here's an example about cars. And I'll just say we've had lots of those. We probably do need more women on the committee. But anyway, you can see here we have a base car, and we've decided we want to be careful drivers. We won't allow it to speed over 100, whatever that might be. But someone has decided they want to have a fast car. And I think someone actually forgot here to actually inherit the fast car from the base car, but assume that part exists here. Just imagine it, public car. And now we have a fast car derived from the base car. The fast car wants to go as far as 169, but the base car is limiting it. So this is one of the main motivations to say that contracts should not be automatically inherited as in other languages, because look, that it just doesn't make sense, and this is a completely legit example. Also, there are some issues. I won't be going into it, but there are design patterns such as mixins and facades, which just where if you automatically inherit contracts, things quickly get out of hand and become irrational. Then stop making sense there. So here that multiverse comes into view again, seeing this as okay, we need to accommodate ourselves to this kind of use cases and not be too dogmatic about things like automatically inheriting contracts. And there are plenty of such examples. We could have again, cars, of course. We could have a car, normally a car needs to be fueled. So if it's not fueled and you try to drive it, you are out of contract. You are violating the contract. But that's not so with an electric car. It doesn't need refueling. And that shouldn't be violating any contract. But then again, perhaps you're designing this all wrong. You should have a kind of a car operation status, which says nothing about fuel and is different between normal cars and electric cars. And we on the first one would have refueling, the second one would have recharging. There's also a car that could be solar powered, and it's always okay to drive it. But wait, is it? What about what happens at night? So yeah, it's complicated. And the last example actually is a very simple one. In multiple inheritance, you have a base class that expects only odd numbers, and another base class expecting even numbers, and you're always gonna be violating the contract of one of those in the derived class that's derived from both of them. And other than contracts, it's perfectly legit to do this kind of multiple inheritance in C++. There's nothing wrong about it. But you can see that in such cases, automatically inheriting contracts makes absolutely no sense. It just cannot work. So as you can see, this is very complicated. And as with other previous features that we saw, there is simply no way to reach any consensus about this for C++26. So of course we made it ill-formed for now. So you cannot have in C++26 contracts on virtual functions, or more to the point, preconditions and post conditions. Some solutions that were considered, a somewhat simplistic one, perhaps in line to some extent with what we've seen so far, would have had contract assertions, only those defined directly in the function itself, as in the derived function, applied, and with no contract inheritance, which the objections were that this might be confusing for those expecting inheritance. The actual proposal that at some point actually did gain consensus before later losing it was something that would have been different than in other languages, which is one of the main reasons why it was ultimately taken out. It would have, remember that slide about color side and Colli side. So the you can look at the color side as the interface. So if you have a pointer to an object in order to get a virtual call, that would be your interface, which was later renamed to indirect. And the Colli side is the implementation. So now you would be able, on any pre or post on a virtual functions, you would specify whether it's indirect or implementation. Those would be contextual keywords, and would apply only to that respective side, color or Colli. There were lots of discussions whether what would be the default if you specify neither indirect or implementation. And I think that was the main reason why consensus ultimately couldn't be maintained about this. It was left for later. So, as I said, it's we won't have this kind of support in C++26. Moving on, compile time evaluation. In many cases, we have all we need to allow the compiler to perform contract evaluations at compile time rather than at the runtime. That's known as constant evaluation. In terms of semantics, we still have the same semantics with different meanings, less options. Ignore is ignore. Observe semantic would translate into a compilation warning. Of course, we're talking about in case of violation. And enforce and quick enforce would make the program ill-formed, which would entail a compiler error. So what happens if a compile time contract violation results in a failed evaluation? So the first case is indeed that the predicate returns false. And this is easy. We have an ill-formed program in the case of terminating contract semantics. Of course, ignore does not evaluate this at all, and observe would give us a warning. The more tricky part is if there was no actual evaluation, because even though this is a context which must be evaluated at compile time, as in a core constant expression, we've inserted a contract which cannot be evaluated at the compile time. The contract itself is not a core contract expression. And in such a case, the program is also ill-formed. We could have said that, okay, we are going to do this evaluation at runtime, but then the entire function is made a runtime function. And as it turns out, this is something that can be detected via Sphene. And then our entire business logic diverges, and then our contracts are not really checking the business logic. Therefore, we have principle 3 that contract concepts do not see contracts. So basically, it says that we cannot at compile time determine there is a contract and what its outcome would be. Therefore, we cannot make such a delay of execution until runtime. Therefore, this also must be ill-formed code. Coroutines. Now we go into real Herbie Dragon land. So let's start from the easy part. Contract assert. This is as usual, just normal code. Even if it's inside the coroutine, no problem here. And we'll have them in C++26. But what about pre and post? So thing is with coroutines that we actually have them. There's something called a ramp function, the thing that's being seen by the outside world, and that ramp function basically just returns some control object, for example, generator, and it does not contain the logic itself that we see in the coroutine, only that control object, and that's the entire thing basically that any pre and post could inspect. The pre could inspect the initial parameters of the initial call only, and that could indeed be useful in some cases. And the post could basically only look at the return control object. It's doubtful how useful that would be, but who knows. The coils and all this kind of stuff inside the coroutine, that's where contracts might really be useful. But right now we don't have them. That requires more work in the future. And if you absolutely must have them, then you must implement your own coroutine framework and place them inside there. And now we get to the really bad part. Okay, so bear in mind this is existing C++, since C++20 when coroutines were introduced. This is the only place in a language where const does not really count. Because of the work coroutines work, we have the coroutine frame, and any const non-reference, as in by value parameter, must be moved into that coroutine frame after the initial call, even disregarding the const. So in this case, the language disregards the const, it moves such parameters into the coroutine frame, and from that point on, the new copy is actually const. But what this means is that the precondition sees the initial parameter, and contract assert, and for that matter also post conditions would see the copies. Now the value would be the same. These are after all const, but if you have to compare addresses, or if you have captured the initial value for a post condition, you would be having a dangling reference. Furthermore, the way coroutines work, the outside world doesn't know it's a coroutine. It only knows it returns some generator or something of that sort. But it could be just a normal function returning a generator. You can't tell it's a coroutine. That's entirely an implementation detail by design, and it may also change at any time, since it's an implementation detail. Therefore, in particular, any precondition and postcondition, if they are evaluated on the caller side, remember that nice caller and callee side chart, the caller side doesn't know it's a coroutine. Any pre and post implemented on the evaluated on the callee side, it does know whether or not it's a coroutine. So with all these issues in mind, the somewhat perhaps surprising outcome is that after some back and forth on this, we do, after all, have contracts in coroutines in C++26, all three types of contracts, but you need to be very careful with that. Preconditions, you're fine there. They will only be useful for inspecting the input parameters in the initial call, but you probably will have some use for that. Same for contract assert. They are normal as long as you don't need to compare parameter addresses at that point with their original address. You're also fine. Post conditions, be very careful there. Most likely, you will have absolutely no use for them. And if you do use them, do not inspect by value parameters. They will most likely be dangling. Just don't do that. Just don't. Undefined behavior. When coupled with contracts, this is one of the big topics that created lots of controversies and brought up lots of concerns. So I will list a few of those. First of all, of course, concerns about undefined behavior in contract assertions. There are several ways to look at this. First of all, when we this relates only to observed semantic, because observed semantic on the one hand does evaluate the contract. On the other hand, it's not terminating semantic, so the following code may be executed if, after a failed contract evaluation. So the first concerns would be that we have those contracts in order to avoid undefined behavior. But with observed semantic, we don't avoid undefined behavior. So since the undefined behavior is still there in the follow-up code, if it indeed has undefined behavior, we may get time travel with an optimizer deciding that the that the contract assertion before the undefined behavior can be optimized out, because it's pretty to assume that the undefined behavior will never occur. That's the nature of undefined behavior after all. So we may lose those contract assertions, which would be bad. We have a new tool in C++26 via P1495. It's called observable checkpoint. So you have a library utility, you place it there. It basically serves as a barrier for undefined behavior having effects in both directions. So this is solved by that. And we also have the opposite direction, which applies to all the semantics, in this case, including the observed semantic, which stipulates that what if we have undefined behavior inside the contract assertion itself? And this might cause the compiler to optimize out the code following the contract assertion, which of course would be a disaster. And those observable checkpoints protect us against that possibility as well. There is no disagreement on us not wanting undefined behavior and side effects in contract assertions. The controversy is whether we should and we could actively enforce such limitations. Obviously, we don't want new undefined behavior in the language. And if we have side effects, this means the contracts have an effect that we're no longer checking actual production code. We're checking some branch of it. And such behavior might discourage current contract adoption. We also have two principles that are relevant here. Principle 13, it speaks for itself, and also principle 6, no destructive side effects. But on the other hand, C++ is C++, and we don't want to create a dialect, as I wrote 2 slides back. One of the there have been cases where some communities have developed dialects of C++, and the community tries to actively discourage that. So we definitely don't want that for contracts. And with the existing language, we can detect undefined behavior only to some extent. It certainly can't be a sweeping thing, and therefore both undefined behavior and side effects are very doubtfully something that can be actively enforced in C++. Having said that, there have been some suggested solutions. The first such proposal worth mentioning was conveyor functions, which proposed a whole list of limitations, such as no side effects outside of body, does not modify the parameters, and nothing with potential UB, which would be a whole sublist on its own. Can only call other conveyor functions, either explicitly marked with a conveyor, new conveyor attribute, or deduced as such. Can only have strict uh, contract assertions. We'll talk about that in a minute. Parameters may only be passed by value, not even by move or by constref. No reinterpret cast, all sorts of other cast conversions, no new or delete. See the idea. There's more probably prohibitions than what you are still allowed to do. And the main point here is that this would have been the only kind of function that would be invocable from strict contract assertions, which would have been a new kind of assertion marked as such. This is kind of the opposite of unsafe code in Rust. We would have the current type of contract would be relaxed contracts, and we'd have strict contracts which would only be able to have those restrictions themselves and to invoke only conveyor functions. Another big issue that is that one of their limitations would have been that if you pass in an object via a pointer, then you must be able to prove via something called stored object address that there is a valid object residing there, not just that the pointer is not null. And that is a big issue. It means that must be provable. You must be able to track all the object. It's very doubtful that that's implementable. What's the origin, the provenance of that pointer? It means most of such code would be unprovable in this way, and this would make it ill-formed. So you get a lot of compiler errors for code that currently works, or seems to at least. Would hinder optimizations, obviously. You would have to compare pointers of doubtful origin. So in some cases, this might actually introduce new undefined behavior, which kind of defeats the purpose. And speaking of defeating the purpose, you would have to adapt existing code bases, lots of work. Many places would then default to relaxed contracts. So what have we done with this? And having so many restrictions in place would make this whole thing just plainly unusable, in addition to probably being unimplementable. As to the whether or not implementable part, a few of the main contract authors got together over a lunch break during the Hagenberg meeting a year ago, because of course lunch is or food is not always a thing in committee meetings. There are more important things, as you can see. And they decided to do a quick exercise to list the list of restrictions that would be necessary in order to be compliant with such conveyor functions. And in order to be able to prove lack of undefined behavior. And they came up with a paper, I think it was more or less 3 pages. That's a small paper. It basically threw out almost everything you can do in the language, and it left us with a few arithmetic expressions, and more or less that was it. This kind of proof that this would really be impossible. That's actually not about the implementability. That's about usability, even if that were something that can be implemented. Now, even assuming we can produce such a UB-free dialect, again, we don't like dialects regardless, we would then probably start arguing over what would need to be the default, strict or relaxed contracts. Thank you again, especially if you've managed to keep up so far. As you've seen, hopefully in both parts of my talk, contracts are a very complicated issue, and there are quite a few more topics that, who knows, maybe there will be even a third part. And so, yeah, we should really appreciate those who did all the heavy lifting here. And let's hold our fingers tight that 2 weeks from now, contracts will pass the final hurdle over in Croydon near London. And then we'll be able to say we have contracts in C++26. Thank you, and now be heading over to Gathertown, hopefully for your questions, assuming I'm not prevented from doing so by external circumstances. Thank you.